This video is about the optical properties of blood. It corresponds to section 22.5 of the Applied Analog Electronics textbook. Now, the reason we're interested in the optical properties of blood is because we want to design devices like this one, a pulse oximeter, or this one, a smartwatch that has a pulse monitor built into it. And that pulse monitor has green LEDs that are flashing on and off there, which you may not be able to see in the video because they may be synced with the video too much. All right, how do these two things work? And how do we choose things like what color LED do we use? All right, let's take a look at the different ways that we could monitor blood. The basic idea is that when your heart beats, the pulse of pressure there results in a lot of blood cells moving with it, and they kind of accumulate at the capillaries or in the arteries just before the capillaries where there's a bottleneck, and then gradually disperse as the pressure releases. So you get an increased blood cell concentration that's synchronized with the pulse. All right, so what do we do to detect that? Well, there's two basic ways to do it. One, if we think of something like the pulse oximeter, we've got a finger here, and we've got an LED on one side and a photocell of some sort, probably a phototransistor, on the other side. And we shine light through the finger. This is known as trance illumination. And the prefix trans here is because it's through. The wristwatch, however, didn't shine light through the entire wrist. The wrist is, on this side there's just a buckle. There's no detector on that side. Both the light and the detector are on the same side. So what you have is the wrist, and then you have the LED and the phototransistor, or whatever the photodetector is. It may be a photodiode or anything that's sensitive enough. And what you do is you send the light in, and you get it scattered back to the phototransistor. And this is known as cis illumination. And now the question is, how do you choose how much light to put in, what wavelength of light, and all sorts of things like that. And it does change depending on whether you're looking at trans illumination or cis illumination. For the trans illumination, you've got to have the light be bright enough that it'll go all the way through the finger or whatever it is you're shining the light through. And for that, you want it to be in a region where most of the flesh is fairly transparent. You don't want something which is only going to penetrate, a tenth of an inch or a couple millimeters if you have to get through the entire thickness of your finger. The other thing that you have, however, on the cis illumination is that you're relying on the light being scattered back. So something that isn't scattered much, that just goes straight through, would not be desirable. You want something that gets scattered back and can be detected on the same side as the light's coming in. Okay, so what do we care about? Well, we care about what things besides the blood cells will absorb the light. Because if the light gets absorbed by other things, then there isn't any light left to be a signal. So let's take a look at the absorption of both the hemoglobin, which is the main thing in the red blood cells that makes them red, and it's what's absorbing the light, and a couple of the other things we might have to worry about. So here are molar extinction coefficients for a number of substances that might be important. oxyhemoglobin and deoxyhemoglobin are the two types of hemoglobin that you have. It's actually one type in two different states, carrying oxygen or not carrying oxygen. Um, and this is what a pulse oximeter cares about, is how much of your hemoglobin that you've got there is oxyhemoglobin and how much of it is deoxyhemoglobin. Because if you're healthy and your lungs are working correctly, you should be getting something over 95% oxygenation. Um, and when it drops below that, it's a reason for concern. Particularly, it's used for anesthesiologists to say, "Hey, the person's not getting enough oxygen. We've got to make sure they get more oxygen now. They're not breathing well enough." If you've got COVID-19 and your lungs are failing, one of the things that's one of the symptoms that's easy to detect is that the oxygenation of the blood drops way down. Now, oxygenation of blood also drops in some other circumstances, like if you're exercising very hard, your lungs may not be able to keep up with the rate at which your muscles are taking the oxygen out of the blood, and so your oxygenation can drop then also. So there's a lot of different causes for oxygenation of the blood to change. What we're interested in here is how do you measure it? And the old-fashioned technique from decades ago was you stuck a needle in the person's veins or arteries and sampled the blood and did chemical analysis. And it was very expensive, invasive, basically very difficult to do. And pulse oximetry basically has almost completely replaced that. And what the pulse oximeter relies on is the fact that oxyhemoglobin and deoxyhemoglobin have different absorption curves. If we take a look at around 940 nanometers here, that's in the infrared, that's where silicon photocells and stuff are most sensitive. In that region, oxyhemoglobin absorbs a bit more light than deoxyhemoglobin does. However, if you look at around 680 nanometers, you can see that the deoxyhemoglobin absorbs much more than the oxyhemoglobin. So if you could compare the the absorption of light at 940 and 680 nanometers, you would be able to sort of back calculate how much of the hemoglobin is oxyhemoglobin and how much is deoxyhemoglobin. Of course, there's a bit of a problem here in that you only want to be looking at the hemoglobin. You don't want to be looking at other things that are absorbing light. And there's a lot of other things. You've got bone, you've got fat, you've got skin. And skin can be quite confusing because people's amount of melanin in their skin varies enormously. And you don't want to be measuring something that's just looking at the melanin when you're trying to measure the blood. So what pulse oximeters do is that they have two different LEDs in them, usually one photocell, and they sort of alternately light up one LED or the other one. And they usually at two different wavelengths, as I mentioned, something around 940 perhaps, and something around 680 perhaps. And then, so they're alternately lighting these things up and measuring how much light is getting through. So they're measuring the absorption at those two wavelengths. But then they don't look at just the DC measurement of one measurement. What they do is they look for a pulse. And then they only take the signal that's the AC component, just the part that varies with the pulse, because that's the part that's due to the red blood cells. The other aspects, the fat, the bone, the skin, don't fluctuate. And so by looking at only the fluctuating part, you can get just the part that's due to the blood, and that then gives you just the hemoglobin, because that's essentially all this at these wavelengths that's absorbing the light is the hemoglobin. So that turns out to be a very useful trick. The pulse oximeter takes a while to make a measurement because it has to detect the pulse and it has to then synchronize its measurements with the pulse so that it can look at just that fluctuating part. Now, I've mentioned melanin a couple times here. I've drawn the curves here for eumelanin and pheomelanin. The actual melanin in skin is a complex polymer involving both eumelanin and pheomelanin, and proteins and all sorts of other stuff. So it's not a very simple thing to measure, but it turns out it's got a fairly smooth curve. Absorbs more at the blue end, which is the short wavelengths here, and less at the red end. But it's a fairly smooth curve, so it's not going to have a lot of peaks and dips the way the hemoglobin does. But you do want to be careful not to try and use too high a frequency or too short a wavelength of light, because the melanin and the blue wavelengths really do get blocked quite a bit more than red or green. So when you're transmitting through the fingers and stuff like that, people tend to work with the infrared and red wavelengths, because the U-melanin is much less of a problem there. But when you're doing the cis illumination for something like a smartwatch, you need to have backscatter. And the trouble is you get much more backscatter at the blue end of the spectrum than at the infrared end of the spectrum. So that you have sort of this tension that you would like to ignore the absorption of things in the skin, but you need backscatter in order to be able to see see light coming back from the blood vessels. And so you need something that'll penetrate sort of the right depth into the body so that it goes through the skin, the subcutaneous fat, and gets to the blood vessels, but scatters back enough from the blood vessels that you can actually see the signal. And that's why a lot of the smartwatches end up using green light, somewhere around 500 nanometers. It's the compromise that works reasonably well at getting sufficient backscattering that the penetration depth into the flesh is sufficient to get the blood, but still getting enough backscatter to read the signal. Now, one problem that some people have had with the smartwatches, was a big problem for Apple when they first released their smartwatch, is that they didn't do sufficient testing on people with dark skin. And they had set the intensity of the flashing LED way too low. And the melanin in the skin was absorbing so much of it that basically there wasn't enough signal left to measure the heartbeat for people with dark skin. And this was it was really bad PR for Apple. It was a really bad design. It's a result of having insufficient diversity on their engineering task force. They didn't even think to test on people with very dark skin. Once this problem came out, they of course went back and did the testing and I think upped the brightness of the LEDs so that it would work. But it was a very embarrassing sort of engineering mistake to make, and one that was so easily avoided too. Anyhow, what you'll be doing for a later lab is to make a pulse monitor. And you'll have a choice of using cis or trance illumination, though the LEDs we have are around 700 nanometers, I believe, so that they optimize more for the cis illumination, so for the trance illumination than the cis illumination. But you can try working either way with it and be able to pick up the pulse. Now, we don't have two different wavelengths of light. We were only using one LED, so we're not going to be doing the pulse oximetry. But the electronics for pulse oximetry is really not very different from that for the pulse monitor. The main differences are in the software processing afterwards, and since that's outside the scope of the course, we didn't try doing pulse oximetry. Okay, I think that's enough on the optical properties of blood.